Hello, good evening. My name is Isabela Marquez, and through this video, I'm going to be presenting my final project for NVIDIA's Jetson course, also called Working Towards Skin Cancer Diagnosis. So a little bit of background about my project. What actually is skin cancer? Skin cancer, as its name implies, is a type of cancer that begins in the cells of the skin, and it occurs when the DNA in the skin cells is damaged, and this can be due to ultraviolet or UV radiation from the sun or from tanning beds, which causes the cells to grow uncontrollably and form malignant tumors, and it can be often seen in the form of little black dots or brown dots around your skin. So what is my final project? For this project, I decided to utilize RevNate 18, which is an image classification model, and just different image detection techniques to classify 7 different types of skin cancer. For this, the dataset that I employed for this project was called HAM10,000, which is the acronym for Human Against Machine, with 10,000 training images, and this was extracted from Kaggle. The link will be attached below. And this just addresses challenges posed by the small size and the lack of diversity in available dermatoscopic image datasets. So my dataset comprises 10,015 dermatoscopic images that were collected from various populations and that were acquired using different modalities, though over 50% of these lesions in the dataset were confirmed through histopathology. I then divided these evenly to separate training and test data. So this dataset serves as an academic training set for machine learning purposes and composing representative cases of all significant diagnostic categories in pigmented lesions. So for this project, the subtypes of skin cancer that I use as categories for my machine learning model were actinic keratoses and intraepithelial carcinoma, also known as Bowen's disease, which I labeled as AKIEC. Then the second one is basal cell carcinoma, which I labeled as BCC. The third one is benign keratosis-like lesions, which I labeled as BKL. The fourth one is dermatofibroma, which I labeled as DF. The fifth one is melanoma, which I labeled as MEL. The sixth one is melanocytic nevi, which I labeled as NV. And the final one is vascular lesions, which I labeled as VASC. So what is a CNN? A convolutional neural network, which is what I use to train my model, are deep learning algorithms that are used to find patterns. So the way they work, this is a layout of how a CNN works. It has an input layer which takes inputs, which in our case are RGB images. Then it has convolutional layers, which basically use filters, also called kernels, to detect features like edges, textures, and patterns in images to then train itself and be able to actually categorize and do its job. Then pooling layers, which reduce the complexity of the information by condensing it. So only the most important information that it found during its training within these convolutional layers is retained. Then a flattening layer, which converts all the result in two-dimensional arrays from the pooling layers and maps them into a single, long, continuous linear vector. So the flattened matrix is just fed as an input to the fully connected layer to classify the image and actually provide an output for the user. Then the activation functions are just used to introduce nonlinearity into the model, enabling the neural network to model complex patterns. And then finally, the fully connected or the dense layers, which are also often called output layers, are just layers that use interconnected neurons with weights and biases that just use features to detect certain things about an image to then classify it and make predictions as an output. So for my CNN model, I used a pre-trained model by the company PyTorch called ResNate 18, which is a convolutional neural network with, as its name implies, 18 convolutional layers. This is kind of what that code looks like when you output it. But yes, for this project, I use ResNate 18, which is often used for image classification models. So for my training progress, I started by doing a round of 13 epochs. And this is just a small graph of what that looked like. And as we can see, I realized that the max or the best validation and training output I got, which what that just means is the most accuracy I got, was around the 17.5 mark at epochs. So I realized that was where I wanted my training to be. And as we can see, the training progress for a machine learning model, especially for image classification, is not linear at all. And that's why it's important to not overtrain your model but also not to undertrain it, which is why you have to be really careful about your training. So this is what my results look like. As we can see, we were able to get this model up to an accuracy of around 98%. In these images, we were able to get results of up to 100% certainty. This percentage just symbolizes how certain, or it's just a value that symbolizes how certain the model was making its prediction. So we can see that we were able to reach 100, 99.96, which if you round it, it's pretty close to 100, and then 91%. So what I mean by showing this is that we were really close to that 100% mark. Now, before I get into how you can use this model and how I can made it, I'd like to take a moment and explain how I created my own dataset. This is a zip file that I downloaded straight from the Kaggle website that is linked below, and as we can see, they provide two folders, one with 10,000 images and a second one with 10,030 images. The only issue is that they're not actually classified by the type of skin cancer or if it's non-benign. However, what they did provide was a CSV file that contains the name of every single image, the category they belong to, as well as the lesion ID, the localization, the sex, and the age. So what I did to fix this problem was I created my own code that basically imports a text file, which is just a CSV file copied into a separate text file, and the folder. This is just for part 1. There's a separate one for part 2. Then I created an empty array in the form of a multi-dimensional list, and this first part of the code just reads through that text file and parses the text, splits and strips it, so that way we can append it into the array, just the name ID and the category, which is all we care about, considering that we don't really need the localization and those other factors in order to train our model. Then I set and define the location of every single class to create folders. And then this part of the code just basically looks at the array, compares the image and the category, then looks for the image in that part 1 file, and then just moves it into the category or the folder that corresponds to that category. And I did that to split it, and then after doing that, I split it halfway through my test data and my training data. Now this is going to be a video demonstration on how you can download my model and try it out yourself from home. In order to do this, you're going to need a working Jetson Nano, which as you can see I have set up right here, that has jetson-inference installed and running. The jetson-inference GitHub will be linked to this video and to the GitHub page for this project, so you can install it and get that running. I also want to show you this dataset. This is the dataset that I used, as was previously mentioned, and as you can see, it's 10,015 images of skin cancer classes and just different types of it. So I'm going to be linking the GitHub for this project in this video, and in order to do it, you're going to want to scroll down to the running this project section, and here you will get a series of instructions on how to do it. So as you can see, the first step is setting up a Nano with SSH connection. Right now I'm running my Jetson Nano on barrel power, but it is connected, and for the purposes of this video, I will be using VS Code, but you can use any software that has the capabilities of making an SSH connection and running a terminal. So to start, we're going to want to run an ls command to check if you have our jetson-inference directory, and as we can see, that is downloaded. We can also see it here, and that just means that we have all the modules and the programs we need to run this model. Next, we're going to run the sudo apt-get update command to make sure that our installer is updated and running our newest version. This might take a second, but as we can see, ours is updated, so once that says done, you're good to go. Now we're going to run the sudo apt-get install git cmake, and what this is doing is basically downloading software that will let us pull and download things from GitHub, and this might take a second, but as we can see, this is installed. So now we're going to want to cd into our jetson-inference directory, then Python, and training, classification, data. And what this is doing is basically just changing directories so that we're located in our data directory that's within jetson-inference, and it's just a directory that's set up so that we can run our models. If we check right now, I only have one data set, which is something that I use for another model, but that should be empty if you just downloaded the jetson-inference folder. And now finally, we're gonna run our git clone recursive command, and this is going to download our data set, which is just images for now, straight from our GitHub. This is going to take some time, but it should only take up to 10 minutes. Now once that's loaded, we should be able to see a skin cancer folder in our data folder, which just has test images, train images, and validation images. Something that's important to note is that for the purpose of saving storage and making it more accessible to everyone on GitHub, I did reduce the amount of training images and left very few in each class, just to give you guys an example. But if you're interested in seeing the full data set, you can access that through Kaggle. So now we can go back to our classification directory by doing the cd ... command, and then go into the models directory. And here we are going to run the git clone command again, and this time we will be downloading our model that has already been trained. Again, this might take some time, but feel free to leave, get a snack, and then come back once this is downloaded. So once you get the done message and you've downloaded the skin cancer, not the skin cancer data, but skin cancer repository, we can actually test this thing out. So now we want to go back to our classification repository by doing cd ... And then just to check if the things download properly, well, first you should see a new model here called skin cancer. But just to check it, you can do ls models skin cancer, and you should see a ResNet 18 file, which is our trained model. So now to actually run this thing, we are going to want to set our net on our dataset values. So you can just copy these commands, and this is just setting our net and dataset variables. And once that's done, we can test this thing out. So to do this command, we're importing ImageNet, which is one of the models that uses image classification that has been downloaded in jetson-inference, and it's compatible with ResNet 18. Then here what we're doing is importing our model. As you can see, this is our input, or we're just telling it what model to use. We're doing net, which is what we just defined here as our directory of model skin cancer, and ResNet 18, which is the name of the file in there, which is actually the name of our model. And then as an input, we are setting them over here. Well, labels, we're also setting them as labels text, since those saved with our data as well. Right here, labels text. And then as for our inputs, we are doing our test folder, because it's in our test folder. It's just already defined that we wanted to come here to skin cancer data, and then test, and then I just left this blank so that you could test it with your own, with whatever you want. So here you want to do the name of the category. So say you want to do one of these, AKIEC, BCC, BKL, TF. You're just picking what category you want to test or what type of skin cancer. And then the name of the image. So you can do mel, mel2, mel3, mel4, .jpeg. So this is an example of what it should look like. So I'm going to be copying and running it to see what happens. So this should really only take less than a minute to run. So we can see here, this is just shows that our image is going through all those convolutional layers. And now that's done, here inside of our output folder, we should see a test 1 image. And as we can see, diagnosed it correctly, BASC. Let's try another example. So now I'm going to be changing it so that I'm going to test an NV image. The same command, I'm just changing the category here. And I'm going to do NV, just NV, the first one. And then the output, I'm going to name test 2 so that we don't delete the other image. And let's run that. Now we have that output here. Let's see what that looks like. So we can see 99.96 NV, it's pretty certain. Now let's try with another image. I'm gonna do BCC. and then I'm going to do VCC4. You can really play around with this. You can do any image, every test folder. I'm going to name this test 3. Every single one of the test folders has 22 images per category. So you can, as for images, you can do anything from the name of the category from just 1 to 22. 1 isn't actually a number, as you can see, but what I mean to say by this is that for your input, you can use anything from BBC all the way to BBC 22. So now let's see that output for our image. So we can see 80%. So that can happen. It may seem as low accuracy. It did diagnose it correctly, but this could be for many reasons, maybe because of the hair, because of the way the image is taking. That is something that can mess with the certainty score, which is what that 80% symbolizes. It really does vary per image. Some will be higher, some will be lower. It really does depend. But the model has trained in a way where it is mostly accurate. I'm going to try with BCC 8 now and see how that goes. And I'm going to name that test 4. As you can see, it did diagnose it at BCC, so it's in the right category with 90%. Again, this can also be because of the way the image is taken. But yeah, you can play around with this. You can do any of the 7 categories, any of this 22 images within those categories, or you could also upload your own image by taking a picture of some mole or something that you want to test and simply saving it to your downloads in your computer and just dragging it into this test folder and then using it as an input. So you can even test your own images and see how that goes. So I want to leave you with some ethic questions, because now more than ever, with this new rise of AI and machine learning technology, it's really important to consider the ethic implications of establishing AI models, specifically when it comes to healthcare. So first of all, what do you feel like is the minimum testing accuracy that an AI model should have to be able to diagnose skin cancer, whether it's positive or negative? Then, in the context of skin cancer, would it be worse for a machine learning system to mistakenly diagnose a cancerous patient as healthy, so to output a false negative, or as cancerous, false positive? And finally, who is at fault if the model produces a false negative or a false positive? Is it the AI company? Is it the doctor? Is it both? Or is no one at fault? Thank you so much for your attention. I really hope you enjoyed. And if you have any further questions, please feel free to leave them in the comments.